Thanks. Hi, everybody. Sorry that I can't be there in person. I'm afraid it's summer holidays in the UK and kids need some entertainment.
England, not in Scotland. They need entertainment. It's no longer
Indeed. All right. Good. So in any case, I'd like to tell you about some recent work. So the talk is based on a couple of papers, although primarily the second one. And so it's a collaboration with a PhD student in Durham, Thomas Barch, and Andrea, who's a member of the collaboration and with you there, I think. And so, well, let me begin with an introduction. And the basic question that we'd like to ask is, if we have a quantum field theory with some categorical symmetries, then how do those symmetries act on and organize the spectrum of operators in the QFT? And so by operators here, I mean very much not just local operators, but also extended operators supported on lines and surfaces and so on, and moreover, operators that are not themselves topological. So we're interested in kind of genuine operators or defects in quantum field theory, and how the symmetries act on them. And of course, there's a very well-known idea, which is, well, representation theory, which applies most commonly to invertible symmetries. So we know from time immemorial that if you have a global symmetry, then your Hilbert space will be in a representation of the symmetry, or perhaps a projective representation. But sometimes we like to think about local operators, for example, and we know that local operators will transform in representations of an ordinary symmetry. We also know, for example, that if you have line defects, then line defects, things supported on a line, Wilson lines, 't Hooft lines, then they can be charged, or they can transform in representations of a one-form symmetry, and so on and so forth. And you can even push this type of picture even further to talk about higher representation theory. So it can be, in fact, that zero-form symmetries can act on line defects, for example, and they transform in two representations of the symmetry. But as long as your symmetry is invertible, it's described by some group-like symmetry or higher group, then representation theory or high representation theory is good and captures how symmetries act on and organize the spectrum of operators. So the question we're really interested in is, well, how do we extend this type of picture to non-invertible symmetries? So for example, you might have a fusion category or a higher fusion category where not all of your simple objects are invertible. And so you have some non-invertible symmetry, but nevertheless, you'd like to ask yourself, how does that act on operators, extended operators that are not themselves topological? So that's the question I'd like to ask. And there's been a lot of hints, I think, and it's known from a lot of sources that in trying to answer this question, studying twisted sector defects is key and important. So what does that mean? It means, for example, we don't just consider local operators, but we consider local operators that are attached to topological lines. And so I should say in my talk, I've tried to be consistent, and that any defect or extended operator which is gray is a topological thing, and anything which is black is not. Well, not necessarily. So
very hard to tell gray from black. I have to
oh, I'm sorry. Does it suck? Okay. Okay. If it's confusing, let me know. And I can explain a bit more. Sorry about that. So indeed, we need to talk about twisted sectors. So you might have a local operator that's attached to a topological line, or you might have a line defect that's attached to a topological surface, and so on and so forth. And studying how symmetries act on these objects, I think, is crucial to understanding the bigger picture, especially when you have non-invertible symmetries. And so the hope is that we can try and capture that type of action in some algebraic structure that we can use to kind of systematize and understand an analog of representation theory, or the right analog. Okay, so I think the answer to this question was given pretty conclusively in a really nice paper in 22 by Linokada, Seifnashri, and Tachikawa. So they were studying a two-dimensional theory that has a fusion category symmetry C. And they gave kind of two answers to this question, two different perspectives. The first was internal, in the sense that it studied objects in 2 dimensions, and it studied how topological defects act on twisted sector operators and so forth. And the second perspective utilized more this sandwich construction of symmetries, where we think about forming a sandwich in the Terayev-Viro theory associated to your symmetry category. So this is a perspective on symmetries that is becoming important, I think. And so on the one hand, from the intrinsic perspective, they explain that you could think about how symmetries act on twisted sectors. This is kind of captured by an algebraic structure called the tube algebra, associated to a fusion category C. This is something that I think has been well studied in the math literature, but its clear interpretation was given here. And so what you're actually interested in is representations of this tube algebra. And so in a way, you've turned your question about a non-invertible or categorical symmetry into representation theory, but it's representation theory for a kind of associated algebraic structure called the tube algebra. And that captures how operators act, how symmetries act on twisted sectors. They also give another perspective where, via this sandwich construction, where all of those twisted sector operators that transform in a given representation are all attached to a given topological line in the bulk 3-dimensional theory, in the Terayev-Viro theory. And so the picture looks something like this. So here's the boundary. That's where the 2-dimensional theory lives, or will live after you collapse the sandwich. And the idea is that representations of the tube algebra are labeled by line defects, topological lines in the bulk. And this kind of captures physically a very well-known equivalence of braided fusion categories between the Drinfeld center of C and the representations of this tube algebra A. And so there are two perspectives. One is kind of intrinsic to 2 dimensions. One utilizes the sandwich construction, but there's a theorem that says that both of those pictures are the same. Okay. So what's the plan? Well, the plan is to try to lift that type of picture to higher dimensions, and also to higher extended operators. So we'd like to be ambitious, and perhaps we can talk about some arbitrary number d of dimensions. And we'd like to consider twisted sector operators of varying different dimensions. And so the type of setup now looks like this. You have some extended operators that are labeled by a dot. They're attached to some topological defects, so they're in the twisted sector. And the way that the symmetries act, by kind of surrounding with, putting your topological defects on spheres and surrounding and linking, the algebraic structure you're interested in is a type of higher tube algebra. So it's a tube N algebra. It's really something that's associated with the sphere that links the relevant operators you're interested in. But that's a thing that you can study. And on the other hand, there ought to be a second perspective where, again, the representations of this higher tube algebra, or the higher representations of this higher tube algebra, are captured exactly by topological defects of the relevant dimension in the bulk topological theory, the Terraia-Vere theory. And so this perspective involving the Drinfeld center or the Terraia-Vere theory in higher dimensions was also explored in a very nice paper of Laksha and Sakura, and I think you'll hear a lot more about that perspective tomorrow. Okay, so that's the plan. I'm not going to try to do everything in D dimensions today. I'm just going to focus on one level up in 3 dimensions and give you some examples, basically. So okay, so the plan is I'm just gonna recap what happens in 2 dimensions, give some examples, and then I'm gonna move on to 3 dimensions and hopefully show that many things are very analogous, but with a bit of higher structure sprinkled in. Okay, so maybe here's a good point to stop and see if there are any questions about the introduction. I'm not sure if I can hear you well, or so please let me know if you can. Yeah. All right.
No hands are up.
Okay, good. Then I'll crack on. So let me just review now what happens in 2 dimensions. So the setup is we have some 2-dimensional quantum field theory, and its symmetries are described by some fusion category. And so we have to give it a bit of structure. Physically, we might ask it to be unitary, but I'm going to focus on, I think I'm just going to need a spherical structure here. So, I don't know what that means. If you like, I can say. Sorry, my phone is talking to me. Okay. Right, so I'm just going to use a spherical structure, I think. So the idea is that there are objects in your category. They correspond to topological lines. So I'll generally label them by X or Y. There are notions of dual, which is like reversing the orientation of the line. And of course, the lines can fuse as well. And so just a bit of notation I'll use. I'll say pi0 of the fusion category. This is the thing that we would say is or isomorphism classes of simple objects, or simple objects module isomorphism. You can think about this as the fusion ring, if you like, of the fusion category. And so in this setting in 2D, the only thing that I really want to look at are local operators. So non-topological local operators that I denote by a dot, but they might be in the twisted sector, which means that they're attached to one of these topological lines. So for each object, each simple object in pi0, we can consider a twisted sector. So genuine local operators that are attached to that given line. And the way that the fusion category acts on those local operators is by surrounding a circle. So you might have some operator in the X twisted sector, and you come along with another simple object A, and the way it acts is by surrounding with a circle here, and it transforms it into another twisted sector Y. So the action might take you between different twisted sectors. This is crucial. And there might even be more data here, so you may have to specify a morphism in your category at the intersection point here. Okay, so that's the kind of picture that you want to capture algebraically. And the way it's captured is by this tube algebra. So it's a nice finite semi-simple algebra. And the way to think about it is that it's generated by morphisms in your fusion category of a particular type. So it's basically pictures like this. So you should read this picture as something that takes an X twisted sector, acts with A, and transforms it to a Y twisted sector. And it's specified by the morphism corresponding to this intersection here, which goes from, if you kind of read it diagonally this way, it takes you from A tensor X to Y tensor A. And then you have to give a product structure, so it's an algebra. you have to say how to multiply these things. And multiplication essentially comes from horizontal kind of composition of these diagrams. So if you imagine stacking these diagrams horizontally in the way that I've drawn them, that's the way you get the product structure here. And then the idea, I think almost pictorially, is that twisted sector local operators will then transform in representations of this algebra. And so that's what you'd like to capture. And well, okay, I said it's a finite semi-simple algebra. It has a bit more structure, I think, but in any case, representations of this thing form a braided fusion category. Okay.
So sorry, unless I'm confused, I feel it could be confusing to say it's an algebra. You mean it's an algebra in C, right? Like if the fusion category C that you started with doesn't have a fiber functor, then you can't regard even the objects of C as vector spaces. So
no, I don't think it's an algebra in C, internal to C. It's just an algebra. It's an algebra in vect, if you like.
Okay.
Okay. Right. I mean, an algebra internal to C would be kind of built out of objects in C at a minimum, right? This is kind of built here out of morphisms. Okay. All right. So that's the kind of intrinsic picture. And it's a nice finite semi-simple algebra, so its representation theory can be studied. Essentially in the business is finding idempotents. Okay, so then there's an equivalent picture where you study this kind of sandwich construction. So now instead of just an intrinsic two-dimensional theory, you imagine building that two-dimensional theory by starting with a slab, where in the middle of the slab, you have the 3D Terraia-Viro theory that you build from C. It's a TQFT, sometimes called the symmetry TFT. And all of the action is going on at what's called the topological boundary, or the gapped boundary here. And so, well, the idea is that the representations, or the irreducible representations of this tube algebra, are in one-to-one correspondence with simple topological lines in this three-dimensional theory. And so the picture looks like this. If you have a collection of operators in various twisted sectors, then transforming in a given irreducible representation, then in this sandwich construction, you should imagine that they're attached to a given bulk line that I call mu. And bulk lines in Terraia-Viro theory are captured by the Drinfeld center. And so that gives it a direct connection with the Drinfeld center. In particular, there's an equivalence of a braided equivalence between the Drinfeld center and representations of this tube algebra. And so the way that works is basically captured by this picture. If you have some simple object, mu, in the Drinfeld center, you'd like to map it to a representation of the tube algebra. And the way you do it uses this picture. You essentially just look at operators at the junction between the bulk line ending on the boundary and some boundary line x. Okay, so this gives a functor in one direction, but this is an equivalence. Okay. So let me give then a couple of examples. So let me first look at the case where the symmetry is in fact invertible. And so here, that means that we're dealing with a finite group, G, and it might have an 't Hooft anomaly, which I'm assuming that I'm in a nice bosonic world, and that's labeled by some group 3 cocycle, alpha. And so the the symmetry category, the fusion category C, is just given by G-graded vector spaces, where the monoidal structure is twisted by this 3 co-cycle. So it's written in this way. And in this case, the tube algebra is a very well-known thing. It's basically a twisted groupoid algebra. So let's see how that comes about. So what generates the algebra? Well, you draw diagrams like this. So the twisted sectors are just labeled by group elements. Now, those are the lines that generate the symmetry. And if you have a G-twisted sector, you act on it with another group element H, it will transform it to another twisted sector given by the adjoint action of H on G. Okay, or conjugation by H. So it's just conjugating the twisted sectors by the relevant group element. Oops. So if I label these pictures like this, you can work out the algebraic structure. It's not too hard to understand. If you remember, it comes from composition in a horizontal way. So you might expect if you have 2 H's and you multiply them, you get the multiplication in the group, and that's exactly what happens, provided you can compose them. It's not always the case. You have to ensure that the twisted sectors match up. That's the reason for the delta function. If they do match up, it's clear that that it's acting twice is equivalent to acting with the product of the group elements. But then the action is slightly twisted due to the anomaly. And so the way to think about this is this tau denotes what's called the transgression of this 3 co-cycle. So it takes a 3 co-cycle on the group, and it spits out a 2 co-cycle on, oops. It spits out a 2 co-cycle on the action on the groupoid for the adjoint action of G on itself. And so what you find is that the tube algebra is basically the groupoid algebra for G acting on itself by conjugation, but the product structure is slightly twisted due to the presence of the anomaly. And so the anomaly is transgressed into a twist for this groupoid algebra. Okay, so that's what it looks like for a group. The representations are also easy to work out, and they've been well studied for a while. So this goes all the way back to Dijkgraaf, Pasquier, and Roche in 91, Dan Fried in 94, and then more recently, Willerton gave a nice geometric interpretation of these ideas. So the tube representations in this case, representations of this algebra, are basically, you can think about them as vector bundles on G with an equivariant action of G on itself. But again, that action is twisted due to the presence of the anomaly. So what's the idea? Well, we're just assigning a vector space of local operators to each group element. That's the vector space of local operators in a given twisted sector. And the group elements act by conjugation. So that gives you a G equivariant structure on the vector bundle. But the action is slightly twisted. It's fairly clear from this that if you're interested in irreducible representations, then they're going to be supported on conjugacy classes, because you can only conjugate a group element among its conjugacy class. Another way to say that is that the irreducible representations you can label by a group element G, and then just studying all of the actions that preserve G. So in other words, H lies in the centralizer of G. And then the irreducibles are labeled by an element of G, namely a twisted sector, and then a projective irreducible representation of the centralizer, where the projectivity is controlled by a 2 co-cycle, again given by the transgression. So another way to say this is all this is really capturing is symmetry fractionalization. You know, we're studying local operators at the end of a line defect, and they don't have to transform in representations of your symmetry, but they might transform in projective representations. Okay. And indeed, this is a well, this was the point of the works at the top, but this reproduces, or this is one description of three-dimensional digraph-Witten theory based on a group in the anomaly alpha. Okay. So that's basically all invertible cases in 2D. You can also play with non-invertible cases. So here's an example. We can take the Ising fusion category with the plus sign. Well, there are two of them. I choose the plus sign for the square root. And so that has a Z2 symmetry generated by a line X, which squares to 1. But there's also a simple non-invertible element, the duality defect N. And that's non-invertible. In particular, it squares to 1 plus the Z2 action. And you can write out the tube algebra very explicitly. It's perhaps not that illuminating, but you can at least see that the structure of the tube algebra in some sense reflects the structure of the fusion rules. So if we have n times n, we get 1 plus x all the way along. But it can transform one twisted sector to another, and then you have to be careful about minus signs sprinkled about here and there as well. Okay, you can also classify the irreducible representations, either by finding idempotence or by studying the Drinfeld center, which is, there should be some citations here. But this is well known in this case that there are 9 irreducible representations in this case. And one nice thing is that they're all realized kind of once by the twisted sector primary operators in the Ising CFT. So if you just go and have a look at the list of those things, well, there are basically 10 of them, and 8 of them transform in one-dimensional tube irreps. This is the list of them here. There's obviously the trivial local operator, there's epsilon, and then there's a bunch of twisted sector primaries. And then, and this is kind of characteristic of this case, there's one two-dimensional irrep, which involves a genuine local operator sigma and a twisted sector operator mu, which is in the twisted sector for the invertible Z2 symmetry. So it's kind of nice that each of the tube irreps is realized in the Ising CFT. And so, for example, one consequence that you can see by staring at this list, for example, is that if you have any local operator that's charged under the Z2 symmetry, the invertible part, any genuine local operator not twisted, then it has to transform in a two-dimensional tube irrep, namely this guy here. Okay, so for the two genuine local operators at the top here are not charged under the Z2. The only way that can happen is if it transforms in a two-dimensional tube irreducible. Okay. So I think that's all I want to say about 2D. And so maybe I'll stop and see if there are any questions.
Nobody has their hand up, Matthew.
Thanks. Okay. So let me now try to explain how to lift this to 3 dimensions and give some examples. So the setup now is slightly different. We work in a 3-dimensional quantum field theory, 2 plus 1. And we imagine now that we can have symmetries that are described by a fusion 2 category C. So what does this mean? It means that we can have both surfaces now and topological surfaces and topological lines. So I'll try to draw surfaces and label them by capital letters X and Y, and lines by small letters X and Y. And again, there are kind of 2 homotopy groups of the category. One is pi 0, and this is now computing simples up to condensations. It's slightly different than for fusion 1 categories. On the other hand, we also have pi1 of the fusion 2 category, and that's computing simples in endomorphisms of the identity modulo isomorphism. But these two gadgets here, pi0 and pi1, they're capturing basically surfaces modulo condensation and lines up to isomorphism. And because we have surfaces and lines now, we can also consider twisted sectors for both of these. In particular, you can have surfaces, topological surfaces that end on line defects, and you can also have topological lines that end on local operators. So we might call them one twisted sectors and two twisted sectors, or more specifically, you might have an X twisted sector local operator or an X twisted sector line operator. Okay. So I want to take these two examples in turn, and I'm going to start with the local operators because they're most similar to what we just discussed. Okay, so let me first discuss twisted sector local operators. So just like in 2D, we have some local operators that look like points. They're attached to topological lines. But now what acts on them? Well, what acts is not topological lines, but we're in 3 dimensions now. So you have to surround this with a 2-sphere. Okay. So we're now mixing up things from pi0 and pi1. Namely, the twisted sectors are labeled by pi1. Those are the topological lines. And the things that can act, they're wrapped on 2 spheres, are labeled by pi0. By surfaces up to condensation. But otherwise, the action is very similar to 2D. You know, the action of surfaces can take one twisted sector to another, and that's basically what we're trying to do, what we're trying to capture. So what are we going to claim? Well, what we'd like to build is again a type of tube algebra. But it's now a tube algebra associated to a 2-sphere because the things that are linking is a 2-sphere. And again, it's a nice finite semi-simple algebra that you want to build out of your fusion 2 category. And this time, instead of being generated by 1 morphisms, it's generated by 2 morphisms. And so the way you build it is like before. You have an incoming twisted sector X, an outgoing twisted sector Y, the elements of pi1, and you have an action of a surface A, which is in pi0. And they intersect again at a point. Points are now 2 morphisms, and so this picture represents a particular 2 morphism in your category C of this form. And again, the idea is very similar. You want to give a product structure on these guys, and the product comes from kind of concatenating these diagrams in a horizontal way. And by doing so, you generate an algebra. And in this case, the twisted sector local operators will transform in irreducible representations of that algebra, the S2 tube algebra. And in this case, this forms a symmetric fusion category, or the representations form a symmetric fusion category.
I think I ask something that troubles me is that you had the spherical assumption on your fusion category in the 2-dimensional case, and it seems if you even want to make sense of the value on a 2-sphere, you need some kind of analogous orientation, and you need more than just a fusion 2 category.
Yeah, I'm gonna use a spherical fusion 2 category.
Oh, sorry, I missed that. I'm sorry. Is that that's a notion that's defined?
I think I want to use it in the sense of Douglas and Reuter. So sorry, there should again be some citations here. So sorry for that.
Okay.
Yeah, but indeed, I certainly want to have things well defined on 2 spheres. Yeah.
Questions? So in 2 dimensions, if you have 4 junctions, sometimes it's ambiguous, right? One might want to dissolve it into like two three-way junctions. But here, is there a way to, or isn't it even necessary to dissolve these things?
Yeah.
Oh.
But I think in the 2D case, if there is a choice, it should be equivalent in some sense, like choosing a different basis for your algebra. In this case, is there a choice? Yeah, I don't think there is, right? Because because the choice comes from kind of the fact that you're in one dimension. You have a choice of this way or that way, right? But here it's an intersection of a line with the surface, so I'm not sure you have such a choice.
But it's still true that you can decompose your junction into the place where the line ends on the two sphere, and then a separate nearby one where it ends. That decomposition, but as you point out, it's kind of obvious. Doesn't depend on what direction you point.
Yeah. There might be lots of choices like this. I think I'm kind of perhaps too quickly assuming that it doesn't matter, but I suspect it doesn't ultimately. Okay. Thanks. More questions? Okay, so I certainly haven't really defined this algebra here. You know, there's a lot that goes into understanding composition, and one has to do that very carefully. And I'm kind of sweeping that all under the rug here. But you know, composition really uses the full data, a lot of the data of your Fusion 2 category. So there's a lot that goes into the composition, but it can be defined. Okay. So again, we'd like to study representations of this, and that's something you can do again by studying nilpotence, or you can get idempotence, or again you can try to lift this to a sandwich construction. And again, the picture is very similar, except now we have a 4D TQFT in the bulk, which is your Teraya-Vero theory of your Fusion 2 category C, or some higher version of it, studied by Douglas and Reuter. And again, the idea is that the representations of your tube algebra in this case are in one-to-one correspondence with topological lines in that theory. And so here, topological lines, well, they're given by not the Drinfeld center, but endomorphisms of the identity in the Drinfeld center. If you like, it's what the Teraya-Vero theory attaches to S2. You might call that the factorization homology of C on S2.
Can I ask a question?
Yeah.
But this thing you're calling Teraya-Vero, that's 3+1 dimensional, right?
Yes.
So it might
That's
work
perhaps an
less
abuse of language. Yeah.
Reuter TQFT or something like that.
Sorry, I didn't hear the last part of that question.
So it could also be called like the Douglas Reuter TQFT if we were trying to avoid confusing with the original.
Yeah, I agree with that and apologize. Yeah. Okay, but the idea is that there's whatever we call it, again, that there's an equivalence this time of symmetric fusion categories between endomorphisms of the identity in the Drinfeld center and representations of this tube algebra. That's the idea. And you can give a functor in one direction. The way it works is in exactly the same way. It's basically capturing this picture here. You take some topological line, it ends on the boundary, and then it's attached to a topological line on the boundary. And the way you build the representation as a vector space is you just compute two morphisms between x and mu projected onto the boundary. Okay, so that's the picture. Let me give you some examples. So again, let me do the finite irreducible. Let me do the finite case first, and then I'll move on. So when you're in 3D, it's slightly more natural in the invertible case to look at a two group, a finite two group. And so here it is. I'll assume that there are two pieces. There's a zero form symmetry, G, which is a finite group. And then there's a one form symmetry, A, which is a finite abelian group. And I'll assume here that the two group is split. So it's like a semi-direct product. And the only thing that's really going on is that the surfaces can act on the lines by some action of G on A by automorphisms that I'll denote in this way. So you've got an incoming line A, the surface acts on it, and it spits out an outgoing line A acted upon by G. And I'm going to look at a particular 't Hooft anomaly. So there are lots of 't Hooft anomalies you might imagine in the setup. I'm going to look at a specific one that's specified by a group to co-cycle lambda on G with coefficients in A hat. So this is something where, well, I didn't try to draw the picture, but it's something where you pass a line through a junction between two surfaces. And that's why you get a two co-cycle. And it gives an extra phase to diagrams like that. But okay, the fusion 2 category is what you might call two vector spaces or G-graded, sorry, two group graded two vector spaces where the monoidal structure is twisted by this lambda. In particular, pi 0 is G, those are the surfaces, and pi 1 is A, those are the lines. And we build the tube algebra in the same way. It looks very similar. It's generated by diagrams that look like this, except now we have a line with a surface acting. But the structure is very similar. Namely, what we get is a groupoid algebra that looks like this. But again, the algebra structure is twisted by a certain two co-cycle on the groupoid that's built out of the anomaly. So the details are slightly different here, but the idea is pretty much the same. Except here, the groupoid is the groupoid for G acting on A. Again, that's a fairly explicit thing, and you can classify the irreducible representations. There's a nice way to think about them geometrically in the same way that we did before. Namely, you think about them as G-equivariant vector bundles on A. You know, we've got a vector space of local operators attached to each line A, and they're acted upon by G. So, and that action is kind of twisted by this two co-cycle. Or if you like, you can view it in terms of a collection. Well, sorry, you can, oops, there we go. If you want to talk about the irreducible representations, again, the picture is the same as before. You pick a line A in the A twisted sector and you look at the group elements that preserve the twisted sector. Those will be group elements in the centralizer of A. Sorry, the stabilizer of A. And then they're labeled, so they're labeled by group elements A and projective representations of the stabilizer with the two co-cycle. And again, this is capturing the idea of symmetry fractionalization. Namely, if you have local operators that sit at the end of a line, they don't need to transform in representations of the zero form symmetry, but perhaps in projective representations. And again, this agrees with topological lines. So in this case, the 4D Douglas-Reuter theory is the 4D Digraph-Witten theory, and this agrees with topological lines there. Okay, let me give an example of that, just to show that this is not so abstract. You can take a gauge theory in 3D whose gauge group is spin, so spin 4K. And this has a symmetry of exactly this type. If you look at spin 4K as a group, a Lie group, it has an automorphism 2 group, which is kind of a 2-group version of D8. There's a Z2 times Z2 one-form symmetry. So for physicists, that's the electric one-form symmetry. And then there's a Z2 that acts by exchanging the factors, and that's charge conjugation, C. And so you can classify the tube reps in this case. There are 5 of them. 4 of them are one-dimensional, and then there's one interesting two-dimensional one. So let me explain how the two-dimensional irrep is realized. Well, it's realized in this theory by studying fractional monopoles. So you want to look at monopole operators in this theory, local operators. Monopole operators are typically labeled by co-characters of the gauge group. And so here, if you take the spinor representations, well, they're characters, not co-characters. What that means is that they're not genuine local operators, but they're attached to topological lines. So they're twisted sector monopole operators. There are two of them for the spinor and the conjugate spinor. Each of them is attached to the generator of these two Z2 factors in one-form symmetry. And they transform in a two-dimensional tube irrep, namely they're exchanged by charge conjugation C. So it's capturing something interesting about these twisted sector monopoles. Okay, let me give you another example, which is non-invertible now. So it's related to the previous example by gauging the whole symmetry, but what you can consider is a gauge theory in 3D whose gauge group is PO 4K, and that has a fusion 2 category symmetry, which is the dual, namely two representations of this group here, of this 2 group. So it's 2 rep of a 2 group. And one interesting thing about it is that if you look at if you look at pi 1, it contains a Z2 factor. There's a Z2 one-form symmetry. But if you look at pi 0, this is the Ising fusion ring. In particular, there's a non-invertible surface, N, just like before.
Can you remind us what 2 reps are in your?
Yeah, so you could think about 2 representations as, I don't know what the best way to say it is, but you could think about it as functors from your 2 group into 2 vect. That might be a way to say it. Does that mean something to you? Yeah. For physicists, it's the symmetry category that you'll get in 3 dimensions by gauging this 2 group symmetry. Okay. Maybe another way to say it is that if you were to start out with the theory above, the symmetry category would be 2 vect of this 2 group. And then what I'm doing to pass from here to this slide is equivariantizing with respect to the action of that 2 group. Might be another way to say it. Okay, but whatever it is, the 2 reps are classified in the same way. Again, there are 4 one-dimensionals and there's 1 two-dimensional. The interesting two-dimensional one is realized again by fractional monopoles. So this time, well, again, you can look at the spinor, the monopoles in the spinor and conjugate spinor, and then you take linear combinations, plus and minus. One of them is untwisted, the other one is twisted sector. So here's twisted for the Z2. And what you find in this case is that the non-invertible surface, N, exchanges these 2 things. So it exchanges the untwisted and the twisted sector. These operators, and so it transforms in a 2-dimensional irrep. Okay, here's another example that's non-invertible but in a different way. You can take your fusion 2 category to be modules or module categories over a braided fusion category B. So this is the case where all the action is coming from lines and all of your surfaces are condensations. And the 2 representations in this case are very simple indeed. Representations of the tube algebra, it's basically just the Muger center of the braided fusion category. And this is just, it's really just capturing the fact, it's just really capturing the possible twisted sectors. You know, in this case, there are no surfaces to act. So all you'll do is you're just enumerating the twisted sectors. And it just tells you that the only lines that can end are those that don't braid. And those are your allowed twisted sectors. So this reproduces something fairly standard about lines. Okay. So in the final part, or in the final however long we have left, I'd like to tell you about twisted line defects in 3D. So everything we've done so far has been kind of algebras. I'm now going to start lifting to 2 algebras. So maybe I'll pause.
Please feel free to take 10 minutes. We started quite late.
Sorry?
Please feel free to take an additional 10 minutes. So you know, a little bit after 1/2 past.
Yep. Okay. Thanks a lot. That should be adequate. Yeah. Okay. So the picture now in 3D is that I want to look at line defects, but they can be twisted sector. So they're attached to a topological surface labeled by an object in the category and now surfaces can act again in a similar way by surrounding with a cylinder, and then they're going to intersect along a one morphism in the 2 category now. So the picture looks something more like this. Now to capture this type of situation algebraically, we need to move up to a 2 algebra. And so we call this the tube 2 algebra, or the S1 tube 2 algebra. It's S1 because S1 is the thing that links, but it's now a 2 algebra because the intersections here are one-dimensional and there can be junctions between them. So a 2 algebra is really more like a monoidal category. So let me tell you what the objects are. Well, the objects are generated by one morphisms in your fusion 2 category C. So again, you might have an X twisted sector. The action is by A, and then it transforms it to a Y twisted sector. And the intersection here is labeled by a one morphism of this form. And then there's further higher data that need to be specified as well. But the idea roughly is the same. It's that twisted line operators will now transform in 2 representations of this 2 algebra. And these 2 representations will form a braided fusion 2 category in this case. Again, the sandwich construction is the same. The idea, except now we're dealing with surfaces in the bulk. So we have a 4D Douglas-Reuter theory based on C. And the 2 representations should be labeled by the topological surfaces in it, which are captured by the Drinfeld center. And the equivalence works in very much the same way, at least at a basic level, at the top level. Okay. So again, let me give some examples quickly. So if you take a finite group G, this is the invertible case. Now it can have an anomaly that's labeled by a 4 cocycle. And the symmetry category would be G-graded vector spaces with the 2 vector spaces with the monoidal structure twisted by alpha. And the picture is very much the same as the invertible case in 2 dimensions. You know, the twisted sectors are just labeled by group elements, and it acts by conjugation among the twisted sectors. And in this case, the tube algebra, or the tube 2 algebra, instead of being the groupoid algebra, it's going to be a categorification of that, which is groupoid graded vector spaces. As a category, it has a monoidal structure, and the monoidal structure is now, twisted by the transgression of the 4 cocycle, which is a 3 cocycle on the groupoid. So yeah, this is something very explicit that one can work with. And the tube 2 representations, again, it has a nice geometric interpretation. So they're now G equivariant 2 vector bundles on the group G, twisted by this 3 cocycle. Or if you want to do things slightly more concretely, and you want to classify the irreducibles, they're labeled by a group element, and then a projective 2 representation of the stabilizer of G with a certain 3 cocycle given by the transgression. And again, this is capturing the same sort of type of fractionalization idea, but it's kind of a higher fractionalization of charges. Okay, and this agrees with the disagrees in this case with the Drinfeld center, as was shown in this paper in 2020 of Kong, Tian, and Zhu. Okay, so let me give you one more example. Again, looking at this case where you have your fusion 2 category is just built out of a braided fusion category. So there are only really lines, all the surfaces are condensations. And in this case, the tube 2 representations, or the Drinfeld center, are given by braided module categories over B. So what's that capturing? Well, there are no surfaces in this case, or there are, but they're all condensations. And so all that's really happening is that you're capturing the action of topological lines on non-topological lines. So it's kind of capturing actions like this. You know, this type of action is giving you a module, is defining a module category over B, but then the topological lines can braid around the non-topological ones. And so this gives the data of a braided module category over B. Okay. All right. So I come to the outlook. So let me give us.
Question.
Yeah.
Can you put a line, topological line around the twisted line? So, I mean, in principle, you measure the charge of the line with a topological line in 3D.
Yeah. So in particular, this will, if B is just a one-form symmetry, I don't know, vector.
In the previous example, actually. So in
Oh,
the
I'm
general
sorry.
example.
Yeah, that's right. That's right. So you can, but that's captured in the higher that's captured in the higher structure that I'm suppressing here. So you're right. So here, right, I'm just looking at the action of surfaces, and you could say, well, what about the action of lines that link, right? Is that what you're asking?
Yes.
Yes, that's captured in the higher structure of the 2 representation. So I'm just studying the top level here. I'm just showing you the top level. So that's all in there. Yeah, that's part of that. Okay. All right, so let me give I think I'm almost out of time, so I'll just give a very quick outlook. So what's the general scheme? Well, you know, the general scheme is pretty much to keep going up into higher dimensions. Looks something like this. You know, the next step is to move up to 4 dimensions, where there are lots of interesting examples. There are also many more subtleties. And so the details are more intricate, but the examples are much richer and perhaps more physically interesting. But you can also do intermediate things that are fun. So you don't need to look at spheres necessarily. You can study tube algebras attached to, say, S2 times S1 rather than S3. And that will be capturing kind of the action on, that will capture the action on loops rather than lines. So you can do more interesting things as well that don't just involve spheres, but products of spheres and other things. And so one other interesting thing that I didn't get a chance to talk about is that much of the structure of these, I believe that much of the structure of these tube representations is being controlled by S matrices or higher S matrices or categorified S matrices in in the sandwich construction. So one way to think about that is we already saw that the irreducible representations of these tube algebras are basically fixed by the kind of transparent actions, so actions that don't change the twisted sector. And these are exactly actions where you can pull the sphere that's acting out into the bulk. And having done so, the action is controlled by the S matrix in the bulk, basically. And so in 2D, with a 3D bulk, it's captured by the standard S matrix. There are examples where, for example, if you just look at twisted sector local operators in 3D, it's captured by a higher S matrix, or that was studied or will be studied in some work of Johnson, Freud, and Reuter. But in general, I think you need even more fancy things involving categorified S matrices to do this, and that's something we're trying to understand. All right, I'll finish there. Thanks.
Questions for Matthew? Constantine?
This is a combined question and complaint. I'm a little confused about the big aim of this. Because if we have a group, we know a representation is actually a set of a linear space. If you have an algebra, you can extend that to a module and actually something. If you have a TQFT, you can easily define a representation as a boundary theory. And then, of course, you can reduce that to have any sphere you like. And based on the analogy with low dimension, reduction of the circle is character theory, and you can call it as higher character theory. It's all very good. I wouldn't define the representation as being their characters, but anyway, that's a matter of taste. But there's a problem behind the taste. For groups, these binary groups and complex numbers, characters help us classify the representations.
Yeah.
That stops being true once you go up. For example, for module categories of a digraph-Witten theory, there aren't even enough of them to span the center. So I'm wondering what the goal is in terms of trying to reduce everything to characters, because we know it can't really be done that way. We need a different kind of calculus here.
So when you say reduce everything to characters and higher characters, I'm interpreting that as one-dimensional higher representations. Is that how I should think about it? I mean, I didn't think I was restricting myself to that.
No, not characters of representations are class functions, not one-dimensional representations. So if you have a digraph-Witten theory, we know the simple modules of subgroups of the group with the trivialization of the cocycle. And if you just do a simple count, they will not span the center of the object. So character theory fails already in its most basic purpose. So I'm not saying it's bad, I'm saying we need a different kind of calculus. That's why I'm asking, how do you see this project helping answer questions like classifying module categories over a fusion category? That I think we don't have a good method for that. And higher up, certainly not. So that's...
Yeah. I mean, I think I certainly agree that the utility perhaps decreases as you go up. I mean, I think like certainly when you go up to 4D, I don't even think that, there's not going to be a finite number of these things. So it becomes perhaps less useful in that sense. I'm not sure, Constantine, I fully understand the objection, but I'm happy to learn more.
I don't know if it's something that can be answered like on the spot, or just want to flag an obvious obstacle ahead.
So I have a question about the line operators in 3+1D TQFTs. I guess they always form some symmetric fusion category, right? So it's always related to some representation of a group or a supergroup. So if it's a non-vertical symmetry acting on local operators in 2+1D, even when it's a non-vertical symmetry, there seems to be some representation theory of a group involved in classifying the representations on how it acts on the local operators. So is it easy to see this group in the purely in 2+1D?
Yeah, it's a good question. I haven't thought about that. Yeah. Yeah, I don't think I have anything useful to say off the top of my head.
There's a question from Sakura on the chat. Can somebody, so can you see it there, Matthew? It says, I didn't fully hear the comment by Constantine, but the main utility is that this characterizes the possible charge defects in QFTs.
Yeah, I mean, I agree with that. I mean, that's the whole point of the talk, yeah.
If it appears there are no further questions, let us thank Matthew again for an excellent talk.